laboratory. Priscila research interest has been the synthesis of and the characterizations of strongly correlated quantum materials, which exhibits emergent phenomena such as complex magnetism, non-trivial topology, and unconventional superconductivity. As a staff scientist at Los Alamos Laboratory, her research further focuses on the application and extreme conditions, high temperature, high magnetic fields, and low temperatures, to novel and puzzling materials towards desired functionality. She graduated from our university and received master and doctorate in physics from Unicamp, São Paulo. Priscila, who is our pride, an example to be followed by our student. I thank you, Priscila, for accepting the Professor Alberto invited to give us a talk, and I give you the word to tell us about your work. Thank you so much.
Oh, thank you very much for the kind introduction, and thank you for the invitation. It's a pleasure to be here. First, I wanted to go there in person, but unfortunately, it's not possible right now, but hopefully in the near future. So today, I would like to talk to you about an overview of the research I have been doing for the past few years, in particular in the search of topology and the physics of condensed matter. I won't go into the details of all the topics because I want to give you an overview, but if you want to learn more about details of the various reports I'm going to present, here is a list of the main results and papers. Okay, for some reason I don't have a point, but I will guide your attention. So first thing I want to introduce is the concept of topological classification. So topology started in geometry. It's a very large field in mathematics that deals with the fact that some spatial properties of materials do not change under small perturbations of the system. So here's the typical example. You probably have seen this picture many times. You can classify objects by the number of holes in them. So for us, actually, Brazilians, it's very easy to understand this because actually a Brazilian soccer ball is actually topologically equivalent to an American football, which is something crazy to us, right? Because we don't call this a ball, and it's not round, but topologically speaking, they are actually the same. And it's quite interesting that this concept of topology came to condensed matter physics very recently. So how is that possible? So instead of looking, for example, at the number of holes in an object, now we're going to look at the band structure of an object or of a material, and we're going to calculate the topological invariant. And this is different for different materials, but let's take here the example of a topological insulator that has inversion symmetry. So in this case, we have the topological classification, which is called the Z2 classification. So you take the parity at each of the high symmetry points in the Brillouin zone, and you have the product of these parities. If the product is +1, you have here on the left a conventional insulator, just a band insulator. But if you have band inversion due to spin-orbit coupling, then your Z2 index is -1, and you have a topological insulator. Because the bulk of the material will be topological, and there is an interface with vacuum or with air, we must have a surface state which closes the gap and it's metallic at the interface. So here it would be the difference between the sphere and the donut. And in this sense, we have here a schematic of a topological insulator that has surface states. And these surface states have a very important property, which is they have a spin textured or protected spin texture against backscattering. So if we have impurities or small perturbations of this material, those surface states won't disappear. And you may be familiar with examples like bismuth selenide. Why are people interested in this? Well, first, the surface states are supposed to be dissipationless or near dissipationless because they are, again, protected surface states. So some interest is there because of, for example, spintronics. But I think the main important aspect here that really got people excited about this is that you can, in principle, have this topological insulator state in proximity to an S-wave superconductor, and that will give rise to exotic quasi-particles called Majorana fermions, and I'll get into this in a little bit. And these particles are really elusive. They there is no evidence that they exist, but there's still a lot to be done. My main area of research actually tries to include interactions in the field of topology. So we want to combine topology that I just described and strong correlations between electrons. And why is that? So in this case, if electronic correlations are important, the single particle picture is not valid anymore. And really interesting things might occur. Tunable topology, you can envision adding magnetism in proximity to some of these materials. You may have really a robust bulk gap that I'm going to actually show you in a couple of slides. There are proposals for topological order and fractionalization of the electronic structure, and getting finally to the possibility of realizing these particles called Majorana fermions. And why are people so excited about these particles? Well, there is something called topological quantum computing that claims to use these particles as their quantum bits, or as their information processing basis. So very schematically, if you have such a particle, so a Majorana fermion is actually defined as its own antiparticle. And when you exchange these particles, and here this is a schematic on the right, if you exchange fermions or bosons, you have a plus or minus sign. But here, if you exchange Majorana fermions, you actually have a phase between them. So these particles are neither fermions nor bosons. You have an extra phase that gives you what's called a non-abelian statistics. And I'm getting into a lot of details here, but it's really to motivate the pursuit of topology and interactions in materials. And really the bottleneck for this proposal right now is the lack of materials for the realization of a quantum computing system. So this is our end goal, but we're really doing basic science. So we want to search for materials that could in the future host such amazing properties. So there are two types of materials that I'm going to talk about today, and they go from one end to from one end of the spectrum to another very extreme end. So one of them are insulators, and the other one superconductors. So starting with insulators, in 2010, samarium B6, which is a correlated insulator. So there are strong electronic correlations here because of the F electrons of samarium. So this material was actually predicted by various groups to be a topological insulator. And this happens because at the X point of the band structure, there is what I was mentioning to in the previous slide, an inversion of the bands. So the parity there is inverted. So if you calculate the parity at the x points, you're going to get a -1 sign, and this should be a topological insulator. One perhaps side note is that it's interesting that one can actually tune this material from a band insulator, so trivial insulator, to a topological insulator by changing the valence of samarium. So samarium can be either 2+ or 3+, and we're going to see in just a moment that in this material we actually have something in the middle. The other end of the spectrum are topological superconductors. Oops, there you go. And just like in topological insulators, we can also define a topological invariant here. But things are a little bit more complicated because we need to know if we are effectively in 1D, 2D, or 3 dimensions, if we have time reversal symmetry breaking or not. And to complicate further, nodes in the superconducting state can also have their own topological classification. So really experimentally, there is a lot to be known here. And I want to start with an experimental guideline because we know that topological superconductors tend to occur in spin triplet superconductors. So often in let's say, BCS or phono-mediated superconductors, we have a spin triplet pairing, so the spins are in opposite directions. But in certain uranium or F electron-based materials, the spins are actually parallel. So you have the possibility of spin triplet superconductivity, in particular close to ferromagnetic instability. So this is going to be the experimental guideline trying to find topological superconductivity, but really there are many, many unknowns. We need to know the superconducting order parameter. That's the basics of any calculation or to understand a new superconductor and whether it's topological or not. The presence of time reversal symmetry, the valence of uranium, just like here with samarium B6, we need to know what the valence is, how many F electrons we have, and finally the Fermi surface. So there are many, many questions to be answered here, and in my group, again, we have been trying to answer some of these questions that I'm going to go into a little bit more detail right now. So let's go in the first. So in the first part with the topological Kondo insulator, I actually have a review that I wrote with Zachary Fisk very recently. It's going to show up, I think, in March in a book called Rare Earth Borides. But it's on archive. And if you want to know more about this compound, please take a look at that. Okay, so let me tell you a little bit about samarium B6. It's an interesting material, but it has a very simple crystal structure. It's just a simple cubic structure. We have samarium ions here at the corners and in the middle, a boron octahedra. So if we look at the periodic table, we know the boron is over here. And from band structure calculations, we know that boron really needs 2 electrons to be happy and complete its shell. And we know that, for example, calcium, strontium, or barium, they are divalent, so they give away 2 electrons. So if we have, for example, calcium B6, we have an insulator, an insulating ground state. And that's exactly what happens in the actual material. But if we go over here to F electrons, so lanthanum, cerium, praseodymium, neodymium, they are all trivalent, so 3+. So they have 1 extra electron and the material is a metal. And for lanthanum, that's very beautifully seen in Hall effect data. You see exactly 1 extra electron per unit cell. But the problem here is samarium. Samarium is actually mixed valence. It's neither 2+ nor 3+. It's 2.6+ from X-ray and photoelectron spectroscopy measurements. So if you were to guess, what would this be, a metal or an insulator? Any takers? No? Oh, come on, guys. This, if you think about the valence, it should be a metal, right? Because you have extra electrons in a unit cell. But no, experimentally, this is an insulator, a very good insulator, actually. The resistance versus temperature, it rises on cooling by several orders of magnitude. So how can we understand this? And actually, there's a very, very nice and beautiful way of understanding this. And that's by looking at the hybridization between the F band and the conduction electron band. So below a certain characteristic temperature called the Kondo scale temperature, these two start to interact, and there is a gap that opens. If the Fermi level lies within this gap, the material will be an insulator. And this can be very nicely described by the so-called periodic Anderson model. So here is the Hamiltonian for that. We have conduction electrons, and then we have a hybridization term, V, between conduction electrons and F electrons. And then we have an on-site Coulomb interaction, U, in the F electron site. So we know very well what's happening at high temperatures and the formation of the gap. Very recently, actually, there are also some measurements of inelastic X-ray scattering showing that the ground state of this material is a gamma-8 state, which is a very nice piece of information. So we know a lot about the higher temperature part. And this material is an F electron system. At high temperatures, it can be described by F electron physics and hybridization. But what happens here at low temperatures, right? This has been a mystery for decades, actually. And very recently, it has been revisited because of the particular prediction of a topological insulating state here in this material. And if the topological insulating state is correct and exists, then there should be surface states in this material. So a lot of investigation has been done in this material at low temperatures to see whether this is actually a surface state. So let me show you some examples. So this is a very clever measurement here of Hall versus temperature. And by measuring the Hall effect at various thicknesses, this group showed for the first time, actually there were two groups that showed with different techniques pretty much the same thing, that below, let's say 4 Kelvin, the conduction is dominated by the surface state. So it's independent of the thickness of the material because the Hall resistivity deals with the thickness of the material in bulk systems, but in the case of a surface state, that doesn't hold anymore. So you can see that the ratio between the Hall resistances here below 5 or 4 Kelvin goes to 1. So I think the community right now, it's been 7 years already, right? So the community agrees, and then there's a consensus that there are surface states. The question that remains, for some time was still a question, is whether this is actually a topological surface state, because surface states exist without the need of topology, right? But one piece of information that is important that showed up more recently is that these surface states are actually heavy, which is something that you would expect if indeed it was coming from samarium, from F electrons. And I won't go into the details of these two papers, but The first one shows that the effective mass of the surface states the mass is heavy, and that is shown by quasi-particle interference and scanning tunneling microscopy. And the second paper is through thermal power measurements. So they both agree that the masses are heavy. And again, this is consistent with the original prediction of a correlated topological insulating state. I want to also touch on the other question that I mentioned briefly before, that we really want to look for robust insulators. For some time, it was a problem in this field of topological insulators that one could have, and still a problem, I guess, one could have impurities really masking the topological states. If the Fermi level is not within the gap, then you're not going to measure an insulating state. So the other question we tried to address was whether this is a clean bulk system. And here is the main result of this paper. This is a very clever technique done by Kurdek's group in Michigan. We are collaborators, and he's an amazing scientist. And they use these Carbinor disk measurements, right, on the sample to be able to separate out surface and bulk conduction. So here's the bulk resistivity of samarium B6 versus 1 over temperature. This is the so-called Arrhenius plot. And you will notice that we don't have the saturation below 4 Kelvin anymore for the pure samarium B6 sample. This is the black line. And it's quite remarkable that the bulk resistivity rises by 10 orders of magnitude on cooling. So these measurements were really able to show that the DC bulk of samarium B6 is clean, and combined with the surface state measurements really show that the bulk is an insulator and the surface states are heavy. However, there's one more piece of information there. There has been a lot of debate on these materials concerning quantum oscillations. So quantum oscillations are a result of the application of a magnetic field in general in a very clean material. And this is a clean material and a metallic material. In this case, we have an insulator. So when people discovered or reported quantum oscillations in this material, there was a lot of controversy and discussion, let's say, because one would ask, how is that possible, right? So many theories resulted from that. But we decided to take another look at this material and at the fact that it may generate quantum oscillations. And we found out, and this is my next figure, that quantum oscillations actually, unfortunately, disappear as we polish the sample down to a very thin slab. And this is very unfortunate because these samples are grown by a technique that involves a third element, and this third element is aluminum. And there is incorporation of aluminum in these crystals. So you can see here in the figures of the samples, it almost looks like a smiley face, right? Smiling at you. But those aluminum deposits, unfortunately, again, generate quantum oscillations that are not intrinsic. So we strongly believe that quantum oscillations are not present in these crystals. And perhaps for the students in the audience, this was actually a negative result that was very unfortunate. And sometimes when you're faced with this kind of problem, let's say, please try to inform the community about the issue, right? It is important when you see something that is perhaps not correct or not accurate, that we disclose this information to the scientific community. So even though this was a negative result, we actually got it into physical review letters. So that was a nice outcome, and I do think that the community deserves to see different aspects of the same problem. So finally, let me tell you about scanning tunneling microscopy. So these are samarium B6 crystals with a little bit of gadolinium in them. So we're looking here at the surface of samarium B6. You can see here the atoms very, very nicely spaced. And these bright spots are gadolinium impurities. And why are we adding gadolinium? Well, if you remember from before, from the first slide, we have a topological insulating state, and that state, that surface state, is in particular, it's protected against backscattering that preserve the symmetries of the system. In this case, gadolinium has a moment, so it has magnetism, it has a large spin, and that breaks actually time reversal symmetry. So you're not preserving the symmetries of the system anymore, and you would expect the surface states to be affected by those impurities. And here we see a DIDV spectra of various points of the sample. So number one is when the tip is on top of the gadolinium impurity, and as you go up, you go away from the impurity. So you can see that number one doesn't have really anything showing up in a pronounced way. But as you go away from the impurity, a little bit of a peak there starts to occur. And that peak is associated with the surface states of this material. So it's clear from these measurements that something is happening when the tip is on top of the gadolinium impurity. And we use this as an argument for the sensitivity of the surface states with respect to magnetic impurities. So I would say this is a busy slide, but it gives you an overview of the types of questions we have been addressing recently and how they help us move forward. And I would say the community, again, everyone agrees that there are surface states here, that they're likely to be topological. However, there's still, to me at least, an open question to be answered. What would be the smoking gun element experiment, or even theory, really, to clearly demonstrate the topological aspects of this material? So I think a lot has been done, but there's a lot to be done still. And with that, let me go to the second part. Let me see how much time I have. Second part of the talk. I'll go over it more quickly, hopefully. So the first part was about insulators. Now we're going to switch gears completely and talk about topological superconductors. So uranium tellurium-2 is another very recent excitement. There is a lot of excitement about it because it's a newly discovered materials or superconductor. I should say the material itself has been known for quite some time, for decades, but only in 2019, and this is the reference at the bottom, it was discovered to be a superconductor. And that's kind of amazing to me. And here's the structure of this material. It's completely different from samarium B6. Now we're talking about something orthorhombic. So A, B, and C, the lattice parameters are different. And they have these interesting chains along the A-axis and dimers along the C-axis. And let me go over the basic characterization of this material, just to give you a flavor for its properties. This is the magnetization versus temperature. Is an isotropic, as one would expect from an orthorhombic material. It doesn't order magnetically. The resistivity versus temperature it increases on cooling at first, when we perhaps have incoherent Kondo scattering, but at low temperatures, the moments start to hybridize and the resistance goes to lower values until at 1.6 Kelvin, it goes to 0. But a superconductor has two properties, right? The resistance has to go to 0, but also it must have Meissner effect. So figure B here shows a diamagnetic signal below 1.7 Kelvin. The heat capacity, which is panel C, shows something also interesting. So below TC, we don't have an exponential behavior as we would expect from a BCS superconductor. We actually have a power law behavior, and gamma value, which is the Sommerfeld coefficient, actually does not go to 0, which is also surprising. So I'll put a pin on this because we also don't know exactly what's going on there so far. NMR measurements or nuclear magnetic resonance measurements do not show any change of the night shift through TC, and this is a pretty good indication that this is not a spin singlet material, because if it were a spin singlet material, the night shift should go to 0 at 0 temperature. But I should mention that more recent results actually show a small but measurable drop, and this could be related to the superconducting D vector of this possible spin triplet superconductor. But unfortunately, only data along the B axis is known so far, so there's still a lot to be done there as well. But I think the main point here is that this is a new material. Even though it has a low TC, it seems to have properties that are not consistent with a simple spin singlet material. And this is really clear in the upper critical field plot. Here is the HC2 versus temperature for various directions, and if you look at the B-axis, it goes almost vertical at about 1.2 Kelvin, really showing that this superconducting material is not limited by the Pauli limit, meaning that the Pauli limit for a singlet is when those spins start to flip, but for a spin triplet superconductor, that doesn't matter. So this is really a strong indication that this is a spin triplet superconductor. And if you remember the first slide I showed you, spin triplet superconductors are actually contenders for topological superconductivity. So there is a lot out there. I think there are more than 80 citations in this from this first science paper here. And let me show you what we have done in my group. First, we measured the heat capacity of this system very carefully to see whether there are two transitions, two superconducting transitions, and actually there are. And this has very important implications because this is an orthorhombic material. So there are no degenerate representations of this space group. So if we have two phase transitions, then we have to have two nearly degenerate competing superconducting instabilities. So that's a very good constraint for any theory, and we started actually with a phenomenological theory, so we can write down the free energy for those two competing instabilities. So two complex order parameters, psi1 and psi2, and we can see what happens under applied pressure, because that's a really clarifying tuning parameter that we can use. And we see that under pressure, the sum of the heat capacity peaks that we can actually measure, it should be constant as a function of pressure, and it is. At low pressures, it's constant, so it is consistent with this phenomenological competition. But at higher pressures, actually, it starts to deviate from what we would expect from that. And this could be because of a nearby magnetic instability. And fair enough, at higher pressures, indeed, we see evidence for the emergence of magnetism, even though we don't have spectroscopic measurements yet. This is consistent with antiferromagnetism. And this is what I'm showing here. We have the phase diagram, temperature versus pressure, and we see the two superconducting transitions. Actually, they cross each other at low pressures, at 0.2 GPa, and one of them disappears, and the purple one disappears, whereas there is a maximum at TC1 at the so-called critical pressure. So there are two critical pressures. PC1 here I'm calling the extrapolation of the magnetism is what we call a quantum critical point. And PC2 is where magnetism and superconductivity merge or are at the same pressure. And close to this quantum critical point, indeed, we can see something that resembles a non-Fermi liquid behavior. So for a Fermi liquid here on the left, we expect a T-squared behavior of the resistivity close to a quantum critical point that may not hold anymore. And in fact, we see something that's close to being linear. Unfortunately, we start seeing the 15 Kelvin or so, we start seeing the tail of that peak at higher temperatures. So things are not so reliable. Unfortunately, we cannot extract an exponent over an order or a decade in temperature. But it's pretty
Priscila?
clear that things. Yes, go ahead.
Sorry, stopping, but the Professor Abudaka is telling us that your slide is not moving.
Really? Which slide?
It's working. If somebody is, it's working to everyone?
Everything is okay in Belgium.
Okay, thank you. So you can keep on. Going on.
Okay.
Thanks. Sorry, Priscila.
No problem. Maybe he can try to leave the meeting and come back. Maybe that would help. Okay. Anyways, at
the end, I give the opportunity for the Professor Musa to talk with you.
Okay. Sounds good. And let me just point out that this particular type of non-Fermi liquid behavior being seen before in antiferromagnetic systems, such as this one, serum rhodinium-5, and again, that resembles a lot of quantum critical point. In that material too, it's so similar that we decided to investigate this coexistence region here between antiferromagnetism and superconductivity. And I won't get into the details here, but the critical current is very small. It's not consistent with bulk superconductivity. So the two are coexisting, but not microscopically. And another point that I wanted to make about the magnetism at higher pressures is that often we have the Fisher-Langer relationship that tells us that the derivative of the resistance will be proportional to the heat capacity jump. And because the heat capacity jump is always positive, that you always have the resistance going down on cooling through a magnetic transition. But that's not the case. That's always the case for ferromagnetic systems, but not necessarily for antiferromagnetic systems, because you can have things, for example, like a superzone gap, when the wave vector of the magnetic structure is not commensurate with the crystal structure. So all of this is telling us that this material is actually close by to an antiferromagnetic QCP. And you may ask yourself, why is this important or interesting? Well, it seems to be really inconsistent with the spin triplet behavior at ambient pressure, right? So if we have a spin triplet superconductor, it's often the case that that's close to a ferromagnetic instability. And again, the spins tend to be parallel in that superconducting state. And here we're seeing a rare example where spin triplet superconductivity seems to be nearby an antiferromagnetic quantum critical point. So that's very interesting, and it has indeed already our results, and as well as many others. This is one example that also agrees with the antiferromagnetic argument, that it has already stimulated a lot of theoretical work that I will briefly touch on in a second. Maybe I'll skip this slide just in the sake of time, so I can get to the theory. So as I mentioned to you, it is interesting that this material seems to be close to an antiferromagnetic QCP, and it would be very important to understand this in light of the superconducting order parameter. So this report here from 2019 actually already touched on this possibility. So here they used density functional theory, or DFT, plus U, so a Coulomb U term as well, to see that actually there are many different combinations of the spin structure that could exist in this material. And as we increase the Coulomb repulsion U, that the ferromagnetic state is actually not favorable. And the interesting thing here is that there are two main systems in the crystal structure. One of them is this dimer I mentioned to you in the C-axis, and the other one is the chain along the A-axis, and those two compete with each other. I'm gonna get a little bit technical for the next five to 10 minutes, but bear with me. So again, as I mentioned to you, this system is orthorhombic, so there are no two-dimensional representations for the order parameter. So here's a table of all the symmetry groups allowed for this particular material. And it's interesting that this very recent result, theoretical result, that took into account our data that I just showed you, actually shows that under pressure, the components here, the URAPs, they change. So they can go from something that's more spin triplet-like to something that has a singlet component and then has a mixed order parameter, which is quite remarkable. Going a little bit further in this, one could also envision that magnetism will show up at higher pressures. Same thing with field, temperature versus field, because we have two different ERAPs. They have different field dependencies, and here is one possibility for their behavior. One open question, though, again, going back to the possible irreducible representations, is that that all sounds nice, but there is one problem here. So we know that the system is two-component, but there are recent results of polar Kerr effect. And without getting too much into the details, I can tell you that the polar Kerr effect gives evidence for time reversal symmetry breaking. So at 1.6 Kelvin here, there is a finite signal that that implies that the system, the superconducting state, breaks time reversal symmetry. And moreover, this signal can be trained with magnetic field along the z-axis. So magnetic field along the z-axis means, if we go back to the table, a B1G symmetry of the system. And the only way to have a B1G coupling is to have a order parameter that is a B3U plus IB2U. And I know this is a little bit technical, but I just want to get to the point that if we take this result into account, the only way really to have the superconducting order parameter written down in a consistent way is this. But I just showed you in the previous slides, both the results from our group point towards an antiferromagnetic component being relevant, and second, other theoretical approaches showing that other combinations of this irreducible representations could be also possible. So I think, again, here, just like in Samarium B6, there's a lot to be done, in particular in this material that's very, very new. Again, both theoretically and experimentally, to narrow down what the superconducting order parameter is, because that is a very crucial aspect to determine, for example, whether this is a topological superconductor or not. So I hope I conveyed to you that the combination of topology and strong electronic correlations really represent a promising path towards the discovery of new phenomena, and in particular, the possibility of either topological insulators or Kondo insulators and topological superconductors. This is something that I'm very excited about and that I wanted to share with you today. So I showed you the example of Samarium B6, which was the first actually topological Kondo insulator candidate. And it's a simple cubic material that shows a very nice insulating DC bulk. I also showed you the example of uranium tellurium 2, which is a more complicated orthorhombic material. Very interesting. There are two superconducting transitions that cross each other, meaning that they're competing. There's a quantum critical point above which magnetism shows up. And there's still many open questions in the field. Finally, I would like to thank my collaborators. Without them, this work would not have existed really. Here on the top left, the strongly correlated electron systems team at Los Alamos. In particular, I want to mention Federico, who's a student who came to work with me for a year, and I do hope he had a good time here. He's from the University of São Paulo, and the theory work was done in collaboration with Rafael Fernandes, who's a Brazilian also, and the X-ray work that unfortunately had to skip was done by another Brazilian. So I really enjoy still working with Brazilians. And the Carbinor disk measurements were done by Kurdek's group, and the STM by both Jenny Hoffman's and Stefan Wirth's group independently. So with that, I would really like to thank you for your attention, and I would welcome any questions. So thank you.
Thank you, Priscila, for your impressive talk. Actually, I have a question in chat. But before the question, I'd like to thank the audience from your brothers from Africa and also South America, some guys. And in the Asia, and of course your friend Milo from Belgium. Professor Musa Abubakar from Nigeria. Please, Professor, can you turn on your mic and give your question to Priscilla? Professor Musa, your mic is off. Can you turn on? Okay, I can give it to Priscilla your question. Priscilla, Professor is you asking about the superconductivity in uranium tellurium.
Mm-hmm.
This is amazing and completely hearing this. Sorry, I'm not seeing too well, but I try to read here. For the first time, because I know uranium to be radioactivity, but how comes when combined with tellurium makes the compound superconductivity? Please, Professor. Do you understand what I'm asking out?
No, I'm not quite sure. Maybe let's see if I can.
Actually, he's telling about the uranium. The uranium is radioactive, and how works the superconductivity when the uranium combines with the tellurium.
Right. So let's see if I understand the question correctly. So even though uranium is radioactive, so we are using depleted uranium, which means uranium-238, which has a much smaller amount of radioactivity. So it's not that we have, for example, self-heating or other issues like damage to the structure because of the radioactive characteristic of uranium. In this case, again, depleted uranium is really stable. You know, you just don't want to eat it, but that's pretty much it. So from the radioactivity point of view, we don't expect drastic changes in this material. And then the other part of the question is, when combined with other elements, in this case, tellurium, and there are other examples, there is uranium, germanium-2, uranium, rhodium, germanium, uranium, ruthenium-2, silicon-2. In all those cases, we have a uranium-based superconductor. So really, why the material is superconducting, I think there is no, let's say there is no right answer, or there is no answer yet. From the theoretical perspective, really, we have an understanding in a case-by-case situation, right? And I would say for uranium tellurium-2, again, this seems to be a spin triplet superconductor. And my gut feeling is that this is related to the fact that we have two low-lying singlet states as our ground state. And this is very similar to uranium, ruthenium-2, silicon-2, right? So I think as researchers right now, we're trying to look at all the uranium-based superconductors out there and try to extract what is similar between them. So this is one possibility, right? But there's, again, a lot to be done. I hope I answered the question.
Thank you. I hope also. Question can be done in Portuguese or in English. As perguntas podem ser feitas em português também. Quem tiver interesse em fazer pergunta à professora Priscila.
If I may, Teldo,
yes.
Ask a question in English.
Yes. Okay.
Thank you, Priscilla, for a very nice talk. Really, a lot of interesting facts I saw here. Maybe first a question about samarium hexaboride. Okay. I was ready to be shocked with these quantum oscillations. I thought you're going to say that there are Shubnikov-de-Haas or whatever oscillations to be measured and map the Fermi surface. At the end, you said that's not the case. But what are, I missed, where did these oscillations come from? What was the source of these oscillations?
From aluminum.
Just from the aluminum. And why they disappear then as you have the thinner and thinner sample?
Because we are removing the aluminum. You can see, so in the first picture here, there are clear aluminum deposits that I kind of mentioned. They kind of look like a smiley face, right?
Yes.
So those silver-ish parts, they are actually aluminum inclusions. So as we go to the second sample, we can still see the aluminum inclusion there, and we still see quantum oscillations. But then the third sample is a very, very thin sample. We see no aluminum, and the oscillations are completely gone. That's the yellow data set. Nothing.
I see. So you had metal, and therefore okay.
Exactly.
You did have quantum oscillations, but not from samarium hexa.
Yeah.
All right. Okay.
But you know, the story is actually more complicated than this, and it's still going on. I can tell you really quickly. So there are two types of samples. So this is one of them. This is the sample I synthesize. They are grown by flux, by aluminum. However, there's a second way of growing these crystals, which is the so-called floating zone method. And in those samples, they also see quantum oscillations. And in that case, it cannot be coming from aluminum because they are not using aluminum flux. So there is still now the question, right? Oh, if there are no quantum oscillations in these samples, how come they exist in the other samples?
Right.
And that's a question that, again, it's still open. Really, as of today, I received a paper about this, a theory paper about this, and the community needs to answer this question. So I just don't know what the answer is. I have my prejudice, but I don't have, let's say, access to those particular crystals, so I cannot prove one way or the other.
Right. But at least the relation to the Fermi surface should be easy to establish, whether it is there or it isn't there, from the frequency and amplitude of those oscillations that are seen. I mean, I haven't seen the data, so I don't know. I'm just speculating here. But theoretically, we can calculate the Fermi surface, and then depending on the direction of the magnetic field applied, we can look at the orbits, maximum orbits of the electrons, and from the area, you know what I'm talking about, the dependence on the energy, possibly the relation can be made and thereby established the origin of the oscillations. So that's,
I agree, but again, 10 different groups have been trying to do this, right?
Okay, so okay.
Yeah.
Yeah, this is okay. I get it. But now that you are on this slide, if I may, one more question about the Carbinor geometry.
You can keep on.
Yeah, so the Carbinor geometry, I suppose the transport was done, or the voltage was measured at different positions between the center and the edge. And in order to probe the surface states, how close the contact needed to be to the edge to say see the difference from the bulk. I don't know if you know what I mean.
So the discs are deposited on top of the crystal and at the bottom, right? Because with the Carbinor disc, you're really just measuring the surface. Then to measure the bulk resistivity, really you need the double-sided Carbinor, which this picture doesn't really show. But if you just have the Carbinor geometry as shown here, just on one surface, then it will be a given, right?
Okay, so no, I missed the point. Okay, so the Carbinor geometry, Carbinor setup where the current is applied is put on top of the crystal. Okay, now I get it. So it's probing No, sorry, I had a different geometry in mind. Okay, okay, I get it. I'll give the chance to others to ask the question, then I'll come back with some more.
Okay.
Alguém mais para fazer alguma pergunta para Priscila? Os alunos podem perguntar como é que foi a carreira dela também, desde que saiu de Cuiabá e chegar em Los Alamos. Acho que os alunos são um pouco tímidos, Priscila.
Eu falo demais, né? Eu posso falar também.
Eu esperava eles responderem a sua pergunta quando você perguntou se era um isolante ou se era um metal, mas eles estavam tímidos. Eles sabiam a resposta, mas estavam tímidos.
Tá bom.
Milo, you can keep on your question.
Don't give me too much, latitude, because then we'll stay here long. Maybe a question about the uranium ditelluride, specifically the theory. Again, I'm not really familiar with the topic, but regarding the two superconducting transitions and the two order parameters, when you model that, how do you model the effect of pressure? And also, how do you model the coupling between the two order parameters without really knowing what they are?
So they are not considering they're coupled, right? Because again, this is orthorhombic, so all the URAPs are one-dimensional. So in some sense, they're not really coupled. The fact that the TCs are very close together actually is an accidental degeneracy in the system. But the effect of pressure is, I think, I actually don't know the answer to that question, how they modeled it. Maybe I can open the paper here quickly.
Yeah, I'm not familiar with the paper. I also didn't have a chance to properly read it, but I'm, very interested in theory, so I was wondering.
Right. So this paper here, the one on the right, is quite amazing. I haven't had a chance to digest it yet. And I say this because they do three different things. So they do a 24-band tight binding model to try to reproduce the band structure of this material. One. Second, they also do DFT plus U, right, to have a consistency check. And three, they also use the periodic Anderson model to cross-check their results. So right now, I don't remember how or where they added pressure to all.
No, enough said. I mean, for DFT plus U, let's say I would know how to do that, but already 24-band tight binding, yeah, that's special enough. But okay, this is the paper I should look at.
Yeah, that one is particularly relevant and recent. It was posted on arXiv less than 2 months ago.
I see. And speaking of this order parameter and different symmetries, is there any indication of chiral superconductivity, some p-wave order?
Yes. Yeah. I unfortunately I couldn't get into those details, but yes, there is a recent Nature publication from Vidya Madhavan's group. So she does scanning tunneling microscopy. So she was able to cleave one of these samples and study the edge states on the surface. And she actually sees something along, I believe, the A-axis that is chiral, that depending on which step edge you are, you probe one direction or one chirality. My God, this is a hard word.
Yeah.
So there is, so the type of it. Go ahead.
Yeah, please go ahead. Sorry.
So there is evidence, but it's not simply let's say, I don't know if you're familiar with other possible topological superconductors, but for example, SRO, or strontium ruthenate, was believed to be a PX plus IPY type topological triplet superconductor for the longest time, for decades, right? Now it's not believed to be that, but I just wanted to point out that in this case, it's not that simple. It's just, again, because we don't have one order parameter with two degenerate wave functions, right? We have two different order parameters that have a phase between them. And again, the Kerr effect measurements seem to tell us that there is a time reversal symmetry breaking. So you have to add the I component there, as they show here.
Right. So that's indeed very special, yeah. And strontium ruthenate that you mentioned is now what, F-wave?
Apparently, yeah.
As of 2 weeks ago.
Until proven otherwise.
Until proven otherwise, but also bismuth palladium. That when you mentioned step edges, it also came to mind as an interesting. But you say this was done, the STM. The
STM has been done. It was published in Nature this year. Let's see.
I don't look enough at uranium-based compounds. I should.
I know that the fact that it has uranium complicates things, but again, as long as you don't eat it, it's fine.
Yeah. Okay, thank you.
No, thank you.
I will give a chance again to people to ask questions.
Thank you, Milorad, for your questions. Priscila, account for the SMBA structures is very similar to the perovskite ones, isn't it? What's the difference? The central element? Yes. Okay, I see.
Yeah, but in this case, I would say there are a few differences. Perhaps one of the obvious ones is that this is maybe not an oxide. If you're thinking about oxides, what kind of perovskite structure are you thinking about?
I know not too much perovskite. Like some couples of perovskite, like strontium titanium and barium, zirconium, and like that. But because in the octaedron, oxygen octaedron, there's no a hard heavy element. It's not a perovskite, this structure, isn't it?
No, yeah, it's not. But it is. I agree with you. It resembles it. The octahedra in the middle kind of resembles what you see in perovskites. But yeah, it's a different structure. I was trying to find what the space group is here.
PM3M.
Yeah, but for the perovskites.
Perovskite, I don't remember. Sorry. And what about the dielectric properties of the systems?
So actually, there's not a lot that has been done recently probing the dielectric function of this.
There is some effect in the superconducting and the isolator topological properties. From the electric properties of this kind of materials.
Yeah, I don't know if I have an answer for you off the top of my head. Again, some dielectric properties have been studied 30 plus years ago, but that's an interesting question. How the dielectric properties play a role in the topology and
yes, that's the question actually.
Yeah, I don't know the answer to that actually. I will have to do some thinking and get back to you.
Okay, thank you. Some guys, any more question for your invited talking? Podemos fazer perguntas em português também. Se não, eu vou agradecer mais uma vez a Priscila. Foi muito legal ter você com a gente, Priscila. Quando vier visitar os seus pais, vá na universidade, que é a sua casa também, será muito bem recebida, como sempre. Quando a pandemia acabar, o professor Milorad vai estar aqui com a gente também, você poderá conhecê-lo e trocar algumas ideias. Ele vai passar um período longo aqui com a gente. E seja bem-vinda, sempre que quiser dar uma palavra com a gente, fazer um outro seminário, falar sobre outro assunto, é só contactar o Alberto ou até mesmo a mim, que a gente marca o seu seminário.
Obrigada, muito obrigada pelo convite. Faz um tempo que eu não vou a Cuiabá, viu? Acho que foi em 2013 que eu fui. Nossa, e o sol tá batendo bem na minha cara agora. Em 2013 que eu fui a Cuiabá a última vez. Em geral, simplesmente pela distância, né? O meu irmão estava morando no Rio de Janeiro e aí os meus pais iam para o Rio, né? E com todo o respeito a Cuiabá, o Rio é um pouquinho melhor, né? Mas eu gostaria muito de voltar para Cuiabá e rever vocês todos. Bom, vamos manter contato.
Com todo respeito ao Rio, né? O Rio de Janeiro não tem louvada. Então, muito obrigado a todos. Thank you for everyone. Thank you, Milorad, for your audience, for the brothers from Africa. Thank you, everybody.
Thanks for the organization. Thanks, Priscilla, for a wonderful talk again.
Thank you very much for the questions.
Have a nice weekend for everyone. Tenha um bom final de semana, Priscila. Muito obrigado. Tchau, pessoal. Fico por aqui. Um abraço a todos.